I want to welcome everybody back to another video session. If we kind of step back and look at what we've been doing for the last few weeks, the first week of the course we did an overview of the PLC, and then we looked at PLC hardware components. We then looked at number systems and codes, and now we're ready to learn how to program this PLC. So we used to use an actual PLC when we were our own college, and now we use simulation software. So I did put up, send you information on where to get that software, and you will need a lab manual. I sent you a copy of the cover of the lab manual, so you want to make sure you take a look at that. And so for the next couple of PowerPoint presentations, we will be talking about programming of the PLC. The PLC, Programmable Logic Controller, uses a language called ladder logic or relay ladder logic. And you'll recognize the symbols because we talked about many of the symbols already. A ladder logic diagram is a symbolic set of instructions. In other words, if you've had maybe another programming course, you may have had a C course or C++. You know, if you write a program in one of those languages, you actually use English words. Well, here we have a set of symbols to represent part of what we call the instruction set. And so the symbols are used to obtain the desired logic that we want the PLC to operate on. You know, there's AND logic, there's OR logic, there's NOT logic. We can use these symbols to mimic or to represent that logic. Ladder logic diagram or ladder logic language is also referred to as contact symbology for the reason I already mentioned. The instructions basically look like normally open or normally closed relay contacts. And so again, it's a symbolic set of instructions, and so you can refer to it as contact symbology. When programming the PLC, there are three fundamental symbols used to translate relay control logic to contact symbology logic. And so you've been exposed to relay control. We've talked about switches. We've also talked about relay contacts, normally open and normally closed. I showed you how you can use switches to mimic or to implement AND or NOT logic. I also showed you how you can use relay contacts to do the same thing. And so now we like to have to implement that in software. So we can actually take a relay control circuit or relay control logic, and we can implement that in this contact symbology. And what you'll see is that the actual ladder logic that we use to program the PLC is very, very, very similar to the relay control logic that you've seen in the past. So what I want to do now is look at the three fundamental symbols used in relay ladder logic. Here's the first one. You might pronounce this IXC instruction, but the proper way to say it is examine if closed. Examine if closed. So what are we examining? Well, remember we talked about the input image table, and I gave you a document to represent the input image table, which is just a way to think about it. You might want to take that document out and have a look at it while we're talking about it. But in the input image table, you had cells, and for us there were 16 cells because the PLC simulation software that you use is word oriented. That word is 16 bits, so for each bit there's a cell to represent each bit in the input image table. And I remember those rows are really registers, and the register can hold a 0 or a 1. If you remember that in digital, when we count, we start counting with 0 and not 1. We can think about cells, individual cells in the input image table, and what this instruction is examining is one of those cells. It's looking for either a 0 or it's looking for a 1. And depending on what it finds, that will affect the truthfulness of the symbol. So we can use the examine if closed instruction to represent any input to the PLC, any input control logic. And so that input can be a switch or push button. It can be a contact, some kind of output contact, or a contact from an internal output. Well, what's an internal output? We'll actually talk about that in a later PowerPoint, an internal output. The examine if close instruction has a bit level instruction. Now it says for the input image table. If you think about it, the input image table, as I mentioned, if you think of it as just a bunch of cells, kind of 16 cells stuck together, and in that cell you can hold a 0 or a 1. And so if something changes in the field, and the field is anything and everything outside of the PLC we refer to as the field. Anything inside of the PLC, we know that's virtual stuff. And so when it says here that the examine if close instruction has a bit level address, what it means is that depending on what's happening in the field, let's say there's a switch that this instruction is monitoring. If that switch is open or closed, it'll represent that with a 1 or a 0. Just a single bit will change in the input image table. That's contrary to other digital devices. I mentioned in previous videos that most other digital devices are byte oriented, not bit oriented. So the smallest level, let's say for your PC, if you have a PC or a desktop, the smallest piece of data that you can grab is a byte, whereas in the PLC we can actually manipulate an actual bit, a single 0 or 1. That's one major difference between the PLC and the normal PC. So that bit level, they refer to that bit as a status bit in the input image table, and it just tells you the status of something being on or off, maybe a switch being open or closed. So you'll see that term status bit. Status bit is examined for an on condition. So this is actually what the examine if close is looking for. Examine if closed. So if the switch is closed, then in the input image table for that particular cell that the switch is mapped to, if the switch is closed, there will be a 1 in that bit position. And if you use the examine if closed instruction, if there's a 1 in the input image table cell that it's mapped to, if there's a 1 there, that instruction will be true. If there's a 0 there, that instruction will be false. And that's the point of these two bullet points at the bottom. So it's better to look at it kind of pictorially. So I have this picture here, and what you see here is this represents one of the rows of that input image table. So we had several rows on the document I gave you. This is just one row of the input image table. Now what this really is it's a register. Remember we talked about shift registers? A register just holds bits, 0s and 1s. And this is the 0 to 15 is 2 bytes, or we said for us a word is going to be 16 bits. So the reason is, again, our PLC has 16 screw terminals on the input image on the input module, and those screw terminals are mapped directly to these bit positions in the input image table. And so here's how this works. First, notice here this I:012-04. This is kind of a generic addressing schema. Some kind of way you have to take the physical device. Let's say it's a switch. The physical switch is tied to the input module, and some kind of way you have to map that physical switch tied to that. Let's say it was tied to the 4th screw terminal on the input. It's labeled 0 through 4, so it would actually be the 5th one. But on the input image, on the input module, there are a set of screw terminals, and the one labeled 04 is the one where we have, let's say, normally we have a switch hooked to it, and if that switch is closed, there will be a 1 stored in this cell. If that switch is open, there'll be a 0 stored in the cell, as you see below. But the point of this slide is that you've mapped this right here through that address. You've mapped it to this bit position in the input image table and to the screw terminal that is hooked up, the physical screw terminal to which the switch is hooked up to. So this is actually monitoring whether that switch is open or closed. If that switch is closed, then the input image table will be a 1 there, and this thing will see that, and that makes this true. If that switch is open, there's a 0 there. It's down here, and when this examines that, examine if closed. So it's actually looking for a closed position or a 1 for this to be true. If it sees a 0, then this will be false. That's our first basic instruction. Our second basic instruction, examine if open instruction. If the examine if closed instruction is looking for a status bit of 1 in the input image table in order to be true, then the examine if open instruction is looking for a 0 in a particular cell of the input image table in order to be true. So it does the opposite as of the examine if closed. So this slide is similar to the one I just showed you. It can represent any input logic in a switch or put button contact from another device, or what we call internal contact. Again, it's a bit level address, so we affect bits and not bytes. And again, we can refer to the status of something. Here, though, pay attention to the last two bullet points. If the status bit is a 0, that is, in that cell in the input image table, if there's a 0 there, and the reason there would be a 0 there is the switch mapped to that position would be open. If there's a 0 there, if the switch is off or open, then this instruction will be true. If the switch is actually closed, then this instruction will be false. So it works the opposite way when you compare this to the examine if closed. So again, pictorially, this is mapped to this 4th bit position, which is mapped to some screw terminal on the input module, and that screw terminal has connected to the switch. And if the switch is open, then in the input image table there will be a 0 in that bit position. This will see that 0. If it sees a 0, then that makes this true. If it sees a 1, that makes this false. The third basic instruction is the output energize. The output energize instruction is used to represent any kind of output, whether it be a motor, relay coil, lamp, no matter what it is, we'll represent it this way in our program. So it kind of looks like, it says here, analogous to a relay coil. Well, the symbol for a relay coil, if you remember, we talked about, it's just a circle, and then we usually name it control relay or main relay. We give it some kind of name. Well, this looks kind of like that. It looks more like a set of parentheses, but you can kind of imagine this to be a relay coil. And so you can see that the input instructions, examine if open, examine if closed, those look like normally open and normally closed contacts. And then this kind of reminds you of, the output energized, kind of reminds you of a relay coil, the symbol for a relay coil. And that's done on purpose so that plant electricians can actually look at your ladder program and this would make sense to them, because they're used to reading electrical diagrams. Well, here is the set of instructions, or how the output energized instruction operates. Again, we can use this to represent any output that's controlled by some kind of input logic. So, you know, as I said before, it could be a relay coil, it could be a light bulb, it could be whatever it is you're controlling, motor. And so this is also bit oriented. And here, this is important. It says any left to right path of input conditions is true, or I should say if any left to right paths or path of input conditions is true, the output energized is turned on. We mentioned before how you read ladder logic, and I mentioned that you read it from left to right. And what you would do is use the examine if closed and or examine if open instructions to get your and or logic. And then what this is looking for is a set of true statements from left to right. And if it sees that, then that wrong is considered to be true. The actual circuit or wrong is considered to be true. And if it's true, it'll turn the output energized. It'll turn that on or make that true. Better look at it from a picture. So here we have a program, This is a one-rung program. We have one row from the input image table, and we have one row from the output image table. Notice that if you can imagine, I have my input module out here, and I got these screw terminals that I can connect wires from switches and buttons to, and each one of those input devices is mapped to a position in the input image table. There's 16 screw terminals out there on that input module, and if you count, there's 0 through 15, there will be 16 storage cells to hold zeros and ones that are mapped to those screw terminals, and they'll hold a 0 if the switch connected to it is open. It'll hold a 1 if the device connected to it is closed. And so right now we can tell the PLC what kind of logic we want to use by using these symbols. So I have examine if close, examine if close, and since they're hooked up in series, you know that's AND logic. And so the only way for this to be true, and true is over here, the only way for this to be true is for both of these to be true. And the examine if close is true when it sees ones in the input image table. So notice the address here is 11, and so that cell is 11. The address here is 15. So this is 15. That's how we actually connect the program that you write, which is what this represents, to a cell or bit position in the input image table. And as I said before, the input module, in this case, would have 16 screw terminals you can connect switches to, numbers 0 through 15 corresponding to 0 through 15 in the input image table. Notice the actual row here has an address, so that's this part of this, and then this is the bit position. So we know what input card and what bit position. We can narrow it all the way down to one single bit. But the way what's happened here is the input module, which we're not showing here in this slide, has switches connected to it, and those switches are closed. I know that because there's a 1 here and there's a 1 there. The switch connected to screw terminal 15 is closed. The switch connected to screw terminal 11 is closed. And since these are both closed, there's a 1 here and there's a 1 there. And since we chose to use the examine if close instructions for both of these, this is going to look at the 1 in cell 11, and if it sees a 1, this is a true. It sees a 1, so this is true. So the first part of our AND is true. Over here, this is going to look at the cell that's numbered 15. It too has a 1. So since this is examine if close, it sees a 1, it's going to be true. Since this is in series, that's AND logic, a true and a true, that makes this output true. So now this is true, and then whatever I have this mapped to, notice this is an output, that's an I here and an I there for input. This is mapped to the output image table, a row in the output image table. Matter of fact, we can talk about the bit number 13. And so, card number 13, bit number 01. And so here, you can see 01. Since this is true, that makes this true. And since this is true, the PLC will put a 1 in the bit position mapped to that particular output instruction. And now what happens is, whatever a screw terminal on the output card that this thing is mapped to, it'll turn that device on. It'll turn it on. Well, what if we change it to a 0? If just one of these changes to a 0, here, this screw right here, the switch to this screw terminal number 11 has opened up. And so now in the input image table, there's a 0. And so, AND has to have two trues. I have a true and a false. That makes this whole rung false. So that's going to make this false. I put a 0 there. And what the PLC will do, if it sees a 0 here, whatever's mapped to on the actual output module, whatever's mapped to this screw terminal, it's going to turn that off. And so here is kind of a summary of those instructions that we talked about. So here I'm using both the examine if close and the examine if open. Here we have a push button, looks like a normally open push button, tied to the input module. Well, since this is open, this represents one cell, one of these. It's one of these cells. This represents the row, but that represents one cell in the input image table. And so right now in that cell, this is open, so that status bit is a 0. Over here, if I push button A down, the status bit is a 1. And so down here, in the case where switch A is open, the status bit is 0. I have the examine if closed instruction. It's looking for a 1. It sees a 0, so it's false. This is looking for a 0. It sees a 0, so it's true. Whereas over here, I will see the opposite effect. I now close this, so my my examine if closed now is looking at that status bit. It sees a 1, so that makes it true. It'll turn this on. This sees a 1, makes that false or 0, so it turns this off. So I would mark this slide. If you understand this one slide here, then you understand the operation of the examine if open and examine if closed instruction, and you'll do well with your programming. You can kind of read this. Ladder logic diagram controls output based on input conditions. That's kind of a given. Control is accomplished through use of a ladder rung. They call it a ladder rung because as your program gets longer and longer, it kind of looks like the rung of a ladder. A rung consists of a set of input conditions represented by contact instructions and an output condition at the end of the rung are represented by a coil symbol. And so all your inputs are always on the left, and the last thing on any rung is always an output. And for now it's a relay coil, but in a couple weeks we'll use some other type of output devices. Each contact or coil is referenced with an address. This actually turns out to be pretty important. We talked a little bit about it, but some kind of way you have to map the screw terminal that your sensor or switch or button is connected to a position in the input or output image table, and then that has to also be mapped to the command, the instruction that you're using. And the way that happens is by addressing. We'll have more to say about addressing a little bit later on. During controller operation, the processor determines the on-off state of the bits in the input image table files, the output or input image table files. So it kind of goes like this. The switch, you got the switch in the field, it's opening and closing. Depending on if that switch is open or closed, there'll be a 1 in that bit position of the input image table. If the switch is closed, there'll be a 0 if the switch is open. And so the program is constantly looking at that input image table as those bits change because of the switches opening and closing. And so it'll evaluate the rung based on the logic that you wrote and the symbols that you use in that logic to give you either a rung that's true or a rung that's false. And if the rung is true, it'll turn whatever device on that you have mapped to. And if that rung is false, it'll turn that device off. The other thing to remember is this happens continuously. The PLC runs in, think of it as a loop. It'll go through this loop. We call a scan cycle that we'll actually define and we'll talk about. Put a little mark on this if you're putting this in your class binder. Input instructions set up the conditions under which the processor will make an output true or false. So in essence, programming a PLC is really simple. You understand AND logic, OR logic, and NOT logic. You understand the truth table associated with each of those. And so you get a true with AND logic a certain way. You get the true with OR logic a certain way. So it turns out we can combine AND OR logic to handle complex logic situations. But when you boil it down, this is what's happening. Input instructions set up the conditions under which the processor will make an output true or false. So no matter how complicated the rung, ultimately we're looking for a left or right set of true statements. And if you see truths, then that output is true. it'll turn that device on. If you see falses, that output is false, it'll turn the device off. When the processor finds a continuous path of true input instructions in the rung, the output energized instruction will remain or become true. We say that the rung is true, rung conditions are true. When the processor does not find a continuous path of true input instructions in the rung, then the output energized will become false or remain false. We say that the rung or conditions of the rung is false. This actually turns out to be pretty important. We'll talk about something called logic continuity. Logic continuity is what this slide is kind of beating around the bush and referring to. Logic continuity is a very, very important concept. A little hard to understand, but once you get it, then it makes all the rest of your programming easier if you understand that we're looking for not current continuity, not how the current flows in the circuit, but what the logic dictates. Logic continuity. We'll have more to say about that later. I'm not going to say too much about addressing. We've been kind of saying a little bit about it in several other slides. So you know there's a way, there's got to be a way for you to map the actual screw terminal, the instruction that you write, and the bit position in the output image table or the input image table. There's got to be a way to map the three together, and you do that through addressing. The simulation software you use uses a certain addressing schema, so we'll just wait until we get into the software before we talk about it. But here is kind of a pictorial representation of addressing. So I got this switch right here that's closed. This is the input module, output module. Anything with a solid line is an actual hard wire. This is an actual device. Anything with a dotted line is virtual. So basically behind the input image table, or to the right of the input image table, to the right of the input module, and to the left of the output module, that's what's inside the PLC. So here is in memory virtual. This is a virtual device. I have the output image table, I have the input image table. Again, we're just showing one row. The point of this is showing you how this is addressed. This is a screw terminal this is connected to. The I here is for input module. The O here is for output module. This number here, the 3, is the number of the module. So I can have a 2, module 2, number 2, module number 1, module number 0. So this is I3. This is my 4th module. So I got the module address and then the screw terminal address of that particular module, which maps to, if you count, if I actually did this right, there should be from 0, this should be bit number 12 when you get over here, if you count it. And so because this is closed, in memory, there'll be a 1. This will update to, if it was a 1, it'll stay a 1. If it was a 0, it'll change to a 1. So this switch right here, being open or closed, affects what's in this register, a 1 or a 0. A 1 if the switch is closed, a 0 if it's open. Now here's a program you wrote, and you mapped it to this bit position, I3. And you use this command, and since you use this command, if it sees a 1 there, then this is going to be true. Now this is you only have one instruction there, so it's not a 1. If I had another one of these, it would be AND logic. We don't have a 1. We don't have a logic command, just other than the inverter that has a single input. It's got to be at least 2. But here, this whole rung is conditional then, depending on the state of this. Basically, if this is a 1, then this is examine if closed, it's looking for a 1. If it sees a 1, it makes this whole rung true, which means that this is going to be true. If this is true, it's going to put a 1. It's trying to show you here in red, there's a 1 in that bit position. Again, addressing is important. I map this bit position to that screw terminal because of these numbers right here. Output module 4, bit position 6. Screw terminal will be number 6 over here. And because there's a 1 there, then whatever's connected to it, which looks like there might be a light, a lamp, then that lamp's going to turn on. So this slide is actually pretty important. This addressing schema looks exactly like what you'll use in your simulation software. It's exactly the same. Matter of fact, the simulator, they call the Slick 500, Allen Bradley Slick 500. The simulation software that you use is modeled after the language and design of this Slick 500. So you'll find that this, look at this and study it. If you understand this, you'll be in really, really good shape. So I would mark this slide. It's important. I don't want to say any more about addressing. I think you'll see the importance of it when you actually start programming. And then this connection diagram, I'm not going to talk about connection diagrams. Study it, read about it. You can look up more information on it if you want. We can spend a lot of time talking about I/O diagrams, but unfortunately we don't have time to do it in the course. Let's talk about branch instructions. Now, if you relate this to logic, you know that when you have these instructions in series, that represents AND logic. If you have instructions in parallel, that represents OR logic. So here I have a set of instructions. I have input A, input B. You can think of this examine if close, and there's my output energize. Since these are in parallel, then that represents OR logic, but they refer to this as a branch. So this is a branch. Now, sometimes you'll end up with a situation like this. This is called a nested branch. I got one branch, E right here. That path right there is a branch, and I got another branch, D, that makes up a branch. And so a branch within the branch is called a nested branch. And in some PLCs you can actually do this, but in some you can't. In yours, in the simulation software that you'll use, you cannot do this. So what if this is necessary? Well, this is an equivalent logic. This has the equivalent logic as the one above. So given this, you can implement this in any PLC like this. All you got to do is repeat this contact. And if you were to put that in the truth table, put this in the truth table, and run the logic, you'll see that they're logically equivalent. So this is actually a pretty important thing to remember. Not so much that you'll have to use it, but I think I asked about it on a quiz or exam or something. So I would mark it and remember that. It'll come back at you. So we mentioned earlier in the video internal instructions or internal outputs, internal instructions, and I'll let you read this. I won't read it to you, but I'll just show you this picture right here. So this internal relay coil. So normally what happens is you have this rung. Here we just have, I don't know why we started counting with 1 instead of 0, but it doesn't matter. Here we have these examine if close instructions, and over here the rightmost instruction is always the output instruction. And normally, under normal circumstances, this would connect to or be mapped to the output module, which has some device, maybe a lamp or motor connected to a certain screw terminal. And if you have a set of truths from left to right all the way over to that final instruction, then it'll be true. Just one false, since these are all ANDed, and this will be false. But here, this internal relay coil doesn't reference anything outside of the PLC. As a matter of fact, if you look at it, internal relay coil, internal relay coil. So what this is trying to show you is that relay coil and this examine if close instruction actually have the same address. So I'm not using addresses here, but this internal relay coil, internal relay coil. If you wanted to, you can give it an address and give this the same address. And now what happens? If 1 through 7 are true, that makes this last instruction true. And since this is true, it makes the first instruction on the next run true. and now your ANDing takes place again. If this is true, if the next several instructions are true, then this last output, it says discrete output, which means it refers to an actual device. This is internal, this is external, refers to an actual device. So now it'll turn that thing on if both rungs are true. If just one of these inputs is false, then this discrete output will be turned off. And so this is actually kind of handy if you have a situation where you don't have enough inputs on the rung and you want to extend it. You can use this method to do it. The other thing is there's other reasons why you could use an internal relay coil. So an internal coil, internal instruction, internal command, all that means is it doesn't reference anything outside of the PLC. It references another location in the input or output image table. So that's important to remember. Now, this slide, actually the next couple of slides, are really, really, really important. This actually has to do with your first lab. If you understand the next couple slides, then your first lab will be really, really easy. The lab is actually easy anyway. It's easy, but you got to explain it. So if you have to explain it, if you understand these next two slides, you'll be able to explain it and you'll do well on it. If you don't understand the next two slides, you'll try to explain it and you won't do well on it. So what do we have here? We have looks like we have PB1, PB2. PB1 is a normally open push button. PB2 is a normally closed push button. And over here we have that's the symbol for a light or lamp, but PL, pilot light. Now it says you will note that both normally open and normally closed push buttons are represented by the examine if closed symbol, and they're referring to this. When students see this, often what they want to do, they'll say, all right, what I want to do is I want to mimic this and this using those contacts. And since this is normally open, well, this contact should be normally open. But since this is normally closed, this will be normally closed. And that's not necessarily the case. What you have to do to get the correct symbology down here is you got to understand the logic of the actual hardwired circuit. You have to understand the logic of it. And so there's this term, electrical continuity. Continuity means continuous. If something has continuity, that means it's continuous. So if I push PB1 down, that closes it. PB2 is already pressed or pushed or depressed. And so current, remember, current or power always flows from left to right. And so we can think of current flowing through PB1 because it's pushed down, then through PB2. That'll light up this pilot light. If I release this, then the pilot light goes off. This is a simple AND circuit. This is always true unless I push it. And this will determine whether the light turns off and on. Since this is always true, this is the only one that I make true or false by pushing it. Of course, I can open this. If I push that, then if this is closed, then I still have a false rung because that's open. But I want here is a path through which current. If I think of current continuity, PB1 has to be pushed in order for current to get from through PB1, then through PB2, then through over to my light. But if I want to mimic this in logic, not current continuity, but logic continuity, then you might think I would put an examine if open instruction here, but what would that do? Remember, these both have to be a 1 in order for this thing to light. I can see the way this functions. The way this functions is as long as I don't push PB2, PB1 controls the pilot light. I push it, the light is on, I release it, it's like a doorbell, then the light is off. I want this to function the same way, but I don't want to think of current flowing. I want to think of logic flow. So if you just go by hardware, if you say, all right, that's a normally open switch, so I'm going to use a normally open contact. That's normally closed switch. I'm going to use a normally closed contact. Then what's going to happen? Well, right now, this is looking for a 1. Since PB1 is open, it's going to see a 0. In the input image table, it will be a 0. That kind of functions the same way, right? The switch is open, it's a 0. If I close it, it's a 1. So this is okay. That's okay. When I push this, I want the pilot light to come on. When I release this, I want it to go off. Well, when I push this, think of a 1. When I release it, you want a 0. That's how this behaves. If this sees a 1 from that switch being pushed, then this is true. If it sees a 0, this is false. It's off. And so this mimics the function, the logic, not the continuity, but the logic function of PB1. But what about this one? Well, this one, if I look at it, it's looking for a 1. It sees a 1. And so this is always going to be true because that switch is always going to be closed. So I'm going to use this. That's always a 1. So now the only thing that's determining whether I have a 1 here is whether that button is pushed or not pushed. If you have put a normally closed contact here, if you say, all right, that's normally closed, PB2 is normally closed, so I'm going to put a normally closed contact there. If you do that, then remember the examine if open, that's what that represents, examine if open, it's going to see a 0. If that's a closed switch, if it sees a 1, it's going to be a 0. It wants to see an open switch, and so it wouldn't work correctly. So if you understand the statement I just made, then you'll go a long way to doing really well in your first lab. So I'll just read it real fast. You will note that both the normally open and normally closed push buttons are represented by the examine if closed symbol. Don't just think because you're using actual physical switches that are normally open or normally closed that your contacts, your instructions or your contact symbology will follow the switches necessarily. You have to understand the logic of the circuit, of the logic of what you're doing to get the correct set of instructions. So here it says what you'll know both of the normally open, normally closed push buttons are represented by the examine if closed symbol. This is because the normal state of an input, normally open or normally closed, does not matter to a controller. This is an important statement. The normal state does not matter. What does matter is that if the contacts need to close to energize the output, then the examine if closed instruction is used, and if not, then examine if open instruction is used. But this term, logic continuity, is important. Since both PB1 and PB2 must be closed to cause the pilot light to come on, the examine if closed instruction is used for both. So again, understand this. Actually, I think the next slide gets in us closer to that term of logic continuity. So I'll pause for a second. You can read this, or maybe you can look at the diagram and see how this works. How does this work? When the push button is open, so it should be a PB1 here. It's PB1. When the push button PB1 is open, the relay coil CR is de-energized and the contact CR1 closed to turn on the pilot light. So here I have a pilot light. This is off. This is de-energized. I know that because this is a normally open push button. So if you remember the way the contacts in the relay work, I have two sets of contacts, the normally open and normally closed. The normally closed contacts on the relay only energize when the coil is powered, when there's power to the coil. If I use the normally closed contacts, then those are energized when there's no power. And this is what this is using. This is the actual, don't confuse this with the program. This is your program. This is an actual hardwire circuit. So I have a CR, control relay, and this is the normally closed contact for that control relay. And so as long as I'm not pushing that button, then this contact is closed and there's power to light up the pilot light. That's the logic of the circuit. If this is open, then there's power to light up the pilot light. if I close this, then the relay contact is going to energize, and the normally closed contact is going to be broken. The relay is going to close. The normally open contacts will close, and the normally closed contact will open. It's going to turn that pilot light off if you do it that way. So what you got to do is study the hardwire circuit and make sure you understand the logic. Again, if you don't understand the normally open, normally closed contact of a relay, you're going to have a hard time understanding this circuit. If you don't understand the relay, you want to go back to, I think, the first or second video of the semester. We talked about relays. We talked about the idea of being normally open or normally closed. But you really want to make sure you understand this diagram right here. So this is open. Control relay coil is not energized. And when a relay is not energized, you can make use of the normally closed contact. So be continuity there. And so there's a path for current to flow to light up the light. If you push this, the relay is going to close, but closing the relay opens up the normally closed contacts. So this pilot light will go off. So as long as that button is not pushed, it looks like the logic says, as long as this button is not pushed, I want that pilot light to be on. So if I want my program to mimic that, if this button is not pushed, that's a 0 in that bit position of the input image table. So I need the logic that says when I see a 0, I want you to be true. Well, that's this one, examine if open. When the examine if open instruction sees an open switch, that makes it true, which makes this whole rung true, which means that pilot light is going to turn on if it's mapped to whatever address this output energized command is mapped to. So if you understand that, then I'm happy. So the most important concept we talked about so far today, it is important to remember that the user program is not an electrical circuit, it's a logic circuit. And in effect, we are interested in logic continuity when establishing an output, not current continuity. Current continuity is a physical path from left to right through which current can flow. Logic continuity is a continuous set of true statements from left to right. Logic continuity and current continuity are not the same. I'll leave this to you to look at these modes of operations. You should be familiar with these. I'm not going to ask about them. You'll have some of these on your simulation software, and you'll become familiar with them just from using the software. So I really don't have a lot to say about these. And I think that takes us to our final slide. You guys have a great rest of the day, and I'll talk to you later.